So there's a way I usually go over this for when I'm TAing this. It's a little more in depth. It definitely helps with understanding, but it takes up a lot of time. So I'll just talk about the problem. If you need more help, you can talk to your TA or talk to me later. So let's start off with this. For that one, they used potassium, right?
Yeah, it was potassium.
Okay, let's just use potassium.
If you want, you can look at it.
No, it's fine. I think I can make up something I can use. All right. And for this fun little experiment, let's say, due to these concentrations, the equilibrium potential of potassium, the Nernst potential of potassium, however you want to describe it, because they're all equivalent, let's say for now it is minus 70 moles, right? So for now, let's say that that's it. Now, does anybody know what patch clamping means for the cell? Essentially, it is a way that we can change the membrane voltage of a cell to be whatever we want. So let's say we're using that technique for the cell, so we can change the cell membrane potential however we want. So let's start off and say, right now we are holding the resting potential at so right now we're holding it at 0. So cell is currently sitting at 0 millivolts, right? The equilibrium potential for potassium is minus 70. That means potassium wants this cell to be as close to minus 70 as it can make it. Due to this, due to the fact that we're holding it at this, no matter how much potassium moves, it's not actually going to be able to change the cell potential. But it's going to move as if it could. So right now, it's moving as if it could change the cell to be minus 70. In order to do so, which way will potassium flow? It is sitting at 0. It wants it to be at minus 70.
Out.
Right. It's going to move outside. Because it's a positive ion, right? It's going to move outside of the cell, which is going to make the inside of the cell more negative compared to the outside. That's going to equal a polarization of the cell, right? Which is going to bring it as close as it can get to minus 70. So good job. All right? Now, everything's the same. But now we are holding the cell at...
Yeah. Right? So the outer one is the very low side, right?
We're now holding the cell at minus 90.
Then work your way in.
So what's going to happen to the potassium? Right. Concentration of potassium is the same.
The one next to you with dollar.
But it wants the cell to be at minus 70. Last time that meant moving out. But this time we're actually lower than the rest of potential it wants it to be at. So instead of moving out, it's going to move in. Make the inside of the cell more positive. It's going to result in depolarization. And this is going to try to bring the rest of the potential to minus 70.
So what do you mean by the concentrations aren't changing?
So what I'm saying is we kept the concentration of potassium the same. So that means it still has the same resting potential it wants to be, the same Nernst potential. Because Nernst potential is only affected by the concentration of the ion. Right? Everybody knows the Nernst equation? So while we're changing the membrane voltage of the cell itself, we're not changing what potassium wants to be. Make sense? So now, what's going to happen?
Not going to do anything?
Nothing, right? The cell's already at where potassium wants it to be at. So potassium's perfectly happy. It's not going to move anymore.
Three different ones are close.
Everyone got that?
Could you explain the negative 90 voltage again while you're moving in?